Right, hello everybody, and good morning or good afternoon, wherever you are in the world. Thank you for joining us. My name's Saul, and I'm going to host this session, which has been put together by RenewablesUK to talk about new ways to monitor subsea power cables in offshore wind. Now, what typically happens in these presentations is that because we're all coming out of this COVID era and people are doing back-to-back Zoom and Teams calls, we'd like to give people a few minutes just to join in, and I can see the number of participants is still zooming up, so we'll give everyone a chance to join us at the top of the hour before we get going. For most of the people in the audience, you'll notice that you are muted, but if you've got questions as we're going along, please use the Q&A tab that's in your Zoom controls, because that'll enable you to type a question, and if we'll try to answer them live as we are going along. If we can't get to them or it's too complex, we'll keep a record of them and we'll either try to address them at the end of the webinar if we've got sufficient time for other Q&A stuff, or we will of course come back to you individually and privately, particularly if it's a complex or specific problem. So please bear with us on that. So as we are waiting for a few more people to join in, some other housekeeping rules, just to let you know that this is one of a series of webinars that we often host at Synaptec, although this time with the help of RenewableUK, and you'll be able to go to our website, which is Synaptec, SYNAPT.EC, so the dot is between the T and the E of our name, where you can find our dedicated YouTube channel, a lot of information backing up some of this stuff, explaining what you've missed in previous ones. But for this particular session, we are recording it. And then after a day, once we've captured that recording, we'll make that available on a private channel for everyone who was able to come along here and join us today only. So you'll have exclusive access to that content for a while before we get to Global Offshore Wind, after which we'll open it up to the general public on an open YouTube channel. Now that said, I won't take up too much more time to let people join. There's plenty of people now on board listening in, so thank you all again for participating. We'll get going with this now, and as I say, please use the Q&A function, and then we'll try to leave time at the end for live questions and answers if anyone's got some. Okay, so today, in the run-up to Global Offshore Wind, where we'll be speaking and exhibiting during the event in Manchester, we wanted to make people aware of this technology and our partnership, which is addressing a fundamental issue about the reliability and longevity and performance terms of subsea power cable systems. So we're going to quickly cover off who we are, of course, and what our companies do, how this technology works and applies, and hopefully that'll inspire you to consider us and come and meet us at our stand and understand this technology in more depth to see how it might apply to your business. As some of you probably already know, I saw in the registrations there are a lot of people who are already familiar with our company and our technology, and some new names and faces too, so delighted to see you joining us for this. We've recently made some announcements where we've been successful in being able to deploy this technology within the last 18 months, from initial trials to demonstrations to larger scale deployments. And now, of course, recently we've won the Dogger Bank A and B cable monitoring contract in partnership with Proserv, which is going to be the world's biggest offshore wind farm. And indeed, very soon after that, you'll also see us talking about deploying demonstration systems on Equinor's high wind floating platform. So there's clear industry interest in this, but we wanted to make sure everyone's aware of it. So very quickly, my name is Saul. As I said, I'm in charge of commercial development, sales and marketing, if you like, at Synaptec. And then alongside me, you'll also see Chris, who's got decades of experience in optical monitoring techniques and DTS background and cable systems in particular, who's now resident consultant and expert within our business at Synaptec on everything to do with condition monitoring and cables in particular. And Callum, who's recently joined our extended family over at Proserv, has come over to us from the offshore renewable energy catapult, where he had a BD role there and does something very similar, holding hands with us to bring our technology to market in offshore wind. So we'll leave this behind for you later on when you have copies of this, so you know who to contact if you need to follow up with us. Now, very quickly, as an introductory point, nobody on this call is surprised, and in fact everyone is on this meeting, because we all know that the single biggest unscheduled operational expense in offshore wind is cable failures, and whether these particular statistics that were gathered by Proserv from Catapult are actually directly relevant to your business or the state that your project or your existing operational wind farm is in kind of doesn't matter. The numbers are enormous. If there are failures, they cost millions, and they can take months in lost production time and vessel costs and equipment and people costs to make replacements. So one of the things we realized a few years ago was that if we combined our technology with a couple of others that are available already in the industry, we'd have a more holistic view of cables and their performance over time, and we'd be able to give, or in fact buy, for the operator and the asset owner a little bit more vital time to anticipate these failures and do something about it before they occur. And the ultimate goal of this technology and the deployment of it is to avoid outages completely and avoid those unintended OPEX events. So basically what you'll see here is a technology that we're developing led by Proserv, or a system integrator called Electro cable guard. Synaptec make a critical component within that, and Chris will explain how we do our part of it and how it all comes together, along with existing traditional technologies like DTS and DAS. But it's a three-way partnership between Proserv, the system integrator, Synaptec, who invented a novel instrumentation technology, and BPP Cables, who of course have a long history in the pathology of cable faults and the investigation and understanding of why they fail. So very quickly about Synaptec, and then I'll get into the meat of this presentation. If any of you didn't know us, we've been around for 7 years now, and most of our focus in the past and traditionally was in transmission. And so we've been involved in digital substation work and protection and control systems and wide area monitoring in transmission in high voltage grids. But more recently, we've moved into offshore wind because fundamentally, we invented a technology whereby you can measure critical parameters like voltage or current, but completely passively. So you no longer need power supplies, lots of space, lots of equipment, or any kind of data networks in order to make a measurement from very far away and bring it back very fast and be able to respond in real time to problems as they arise. So it's about passive sensors that are networked through the optical fiber that's available in all subsea power cables. And it's about reducing the capital cost of the footprint of instrumentation, which then in turn helps with reducing and avoiding outages and optimizing things like scheduled maintenance costs. So there's quite a few customers that are involved in this in different areas of transmission, offshore wind, even industrial and rail applications. But today, I want to hand over now to Chris, and he's going to talk you through what are the causal factors in subsea power cable failures that will actually be detectable by our systems so that people can understand how we help. Chris?
Thank you, Saul. Hi, everyone. I think I just want to put some context around this to actually look at, the challenges that we have with regards to high voltage cable monitoring before going into what is basically an overview of the technology and how we are applying this within the sector. So I make some reference as well to some terms in terms of technology, conventional technology like DTS and DAS and real-time thermal rating software and fiber grating technology. We can explain a lot more of that in more detail, but I need to give you an overview of this going forward. So to date, there's a limited amount of cable monitoring data available today because the data that's being collected is not necessarily enabling prevention of failure and those associated costs of failure. So it's we're referencing this in terms of data that's being gathered, cited on this slide actually from data that we gathered from DNV, other data sources as well from existing farms that is protected data, etc. But the general view is that there's a significant number of failures occurring, and that this particularly needs to be addressed. So conventional solutions focus on the cable itself and not on the terminations, where the majority of failures have been reported to date. A little overview of the kind of conventional technologies that are being used. mostly on export cable, I would suggest today. But you know, as the demand for monitoring and preventative technologies actually increases, then there's a much more focus on the inter-array cables. So DTS in terms is effectively used in the fiber then as a fiber inside a power cable as an effective distributed temperature sensor, measuring temperature profiles, whatever, along the cable. So it's very useful in terms of looking for hot spots, cold spots that might be a symptom of cable deburial, you know, and also for its use with real-time thermal rating. In a similar vein, we have distributed acoustic sensing. So acoustic, again, using fiber that is deployed within the power cable itself to actually look for movement in the cable that might be caused by some third-party interference. And both of those technologies are used to some extent actually for fault detection, but due to their nature in terms of a temperature event or an acoustic event, tends to be actually rather close to the point of failure. And not only that, but you know, it's applied to the cable and it's never applied to the terminations. That's a feature of the technology itself. So in terms of periodic ROV surveys are used on a regular basis over the lifetime of the wind farm to help minimize risk and reduce the kind of exposure to cable failures. So, and this is an accepted capital expenditure in the O&M budget. You know, there can be a significant expenditure over the lifetime of the wind farm with you know, like a single week-long survey can cost somewhere, you know, upward of, you know, £500,000 to £1 million. So it kind of begs the question, you know, is there a better technique, whatever that can be used, that may be more effective in terms of mitigating, you know, those problems? So effectively, you know, what we're actually looking at here in terms of this solution, it's, you know, it's driving the need for a more comprehensive and more holistic means of providing kind of cable condition monitoring. So that's including the cable and also the cable joints, cable terminations in particular, to provide a kind of more cost-effective condition-based kind of maintenance strategy going forward. There's a strong demand that such a solution would ideally be passive, you know, kind of increasing its effectiveness, but you know, reducing its overall kind of cost of ownership. So to that end, you know, we're asking, wouldn't an improvement to like this conventional technology that's currently being used, you know, be able to improve the way of actually reducing outage costs and improving availability of field. So how does Synaptec address these monitoring failures? Well, effectively by applying small footprint sensors at every termination and as necessary at every joint. You know, devices are synchronously interrogated, you know, and data from both kind of electrical sensors and mechanical sensors, mechanical like temperature, strain, vibration, you know, are all processed in unison concurrently across field. So all of that providing earlier warning of failures, provided accounting for, you know, these kind of main environmental factors. So subsea cables deployed in offshore wind farms have to endure a uniquely harsh environment. It's not solely due to the environment, maybe salt-laden atmosphere and constant pressure of water ingress into cable infrastructure. Terminations are a relatively weak point throughout wind farms as they, you know, become a focus of electrical stress, resulting, you know, in ohmic overheating and degradation. So this this harsh environment, you know, with fast transient harmonics, so all of that is continually stressing and wearing cable infrastructure. So the concept here is actually to buy more time in avoiding failures, you know, by you know, this kind of knowledge base, whatever, to enable more, well, as the knowledge base increases, then it becomes actually more effective then at managing the operation and maintenance cost of cables, because we know what to expect. From an operational point of view as well, some of the additional benefits of this then are to provide more accurate modeling for real-time thermal rating software, because by its nature, by some of the applications that we're looking at here, you know, they've been able to actually track circulating currents, which believe are actually significant by nature of the design and earthing arrangement between turbines, and that's not something that's accounted for currently in real-time thermal rating systems. So this graphic is really just to kind of summarize where what this looks like in terms of kind of normal operation, and all the effective transients, power quality issues, load cycling, cable losses directly occurring over the life, and as these age, with the potential like for water ingress and whatever, and for that to create corrosion as we move to the right-hand side, to result in this failure event. And so the further in time that we actually, we progress there to the right, the further that increases the potential cost for repair. So looking at where conventional existing technologies are applied, if we look at inspections in ROV, yeah, unlikely to catch problems. I mean, that's a periodicity really of, how often are ROV inspections, required. Is it like once every 4 years? Does that apply differently on export cable as opposed to inter-array cable? These are relatively expensive and risky, so the question really is one here where, could the cost of an ROV be mitigated, by the deployment of a more accurate and holistic cable monitoring solution? The application of existing technologies in terms of DTS and DAS systems, again, those technologies are not applied on terminations. They can't be applied really on terminations by the physics, the nature of those technologies. And so, budget is actually being allocated for that purpose, for the purpose of monitoring, but it's actually missing an awful lot of the failure events. So the argument here is to say, well, if we can actually combine and actually help with that, then we can see things much, much earlier. And again, there's always discussion when it comes to monitoring of cables and faults. It's something, the topic of PD monitoring always comes up. So that again is a technology that requires remote electronics at various locations. It's expensive in terms of real estate as well, in terms of what hardware has to be located at those places. It's quite subjective, I think, as well. So that's why we don't see that many permanent installations of PD monitoring. So that their effectiveness is reduced. So the concept here is the application of Synaptec's distributed electromechanical sensing to look at these kind of earlier causes of failure events that may be picked up, by DTS, DAS, and those events that eventually transpire into PD, that are as in harmonics that are within the infrastructure that eventually cause that wear and tear that will result in longer term kind of PD events. So a little explanation then with regards to distributed electromechanical sensing and what works. So this technology is based upon fiber Bragg rating technology. The fiber Bragg rating technology has been used for many, many years in both telecoms industry, but in terms of sensing applications, I mean, certainly it's got a lot of applications in defense and also in oil and gas. And fiber Bragg rating technology traditionally then is, each of those sensors effectively has its own wavelength, and they traditionally have actually been used for vibration, for strain, and temperature. So each of those sensors will respond with a different measure arm. And what we've been able to do at Synaptec then, as Saul said, is to be able to add current and voltage to that mix. So we can have an array of different sensors connected to a similar fiber, with up to 30 electrical sensors, current and voltage sensors on a single fiber going out to 60 kilometers within the interrogation system, sitting, let's say, in the offshore substation. So it's scalable from that point of view. When we look at the sensors itself, what we're doing is we are interfacing to existing instrument transformer infrastructure, whether it's CTs or VTs. And well, the technology that we've developed is able to take the electrical output of the transformer and convert that to an optical signal, so that the only connection that we have in and out of each device is fiber. So we're working with those sensors. They're both in the bottom right. We have a current sensor, we have a voltage sensor. In applications where there is existing CT and VT infrastructure in place, we would use that three-phase secondary unit to effectively connect into the existing CT, VT infrastructure. And again, that box has simply fiber in, fiber out. So it enables us to be able to retrofit quite effectively. Reliable in terms of that there's no recalibration or maintenance required, no measurement quality issues with regards to strong electromagnetic fields, whatever that we have for that. We've done accelerated aging tests on the sensors that have taken us back to 140 years on the sensors, so that's as passive as we can get. Secure in terms of all of there's no effective data here, because what we're actually picking up from each sensor then is a light signal that's bounced back to the interrogation system that takes that, processes that data. And by the nature of the sensors themselves, you know, so there's a lot of cost saving then in terms of, you know, any kind of additional remote hardware, you know, that's required in terms of telecommunications or power supplies, IEDs, or with data syncing issues, you know, across multiple locations. And in fact, you know, that can be split into multiple, you know, there's various architectures actually are available, but you know, there's a limitation on the number of sensors that can be connected. But overall, there's a huge cost saving in terms of the amount of hardware that's deployed and the associated cost of actually maintaining that hardware as well. That's totally eliminated. So when we look at a system that's interfaced then to an array of sensors, an interrogation system that, you know, that we're actually sampling these sensors then periodically. So we have a means of synchronously sampling, you know, these strings at up to 14.8 kilohertz. Typically in terms of the electrical sensors that we're using, you know, in terms of current and voltage, you know, we sample at 4 kilohertz. So 4 kilohertz on a 50 hertz system allows us to see out to the 40th harmonic. When we're looking at these other measurements, then, you know, in terms of temperature and vibration and strain, there's no real requirement to monitor them at that frequency. So we're able to actually use interrogation systems that are more specifically targeted at those mechanical sensors. But we combine everything so that everything is published, you know, in one kind of data stream then from the interrogation system. So we're looking then at analytics, you know, from all of these data sources, but over if you like multiple time scales. So, you know, in terms of, you know, the current and voltage sensing that we're looking at, you know, this millisecond kind of sampling, you know, the technology was originally developed for protection of transmission circuits. So now we're actually looking at, you know, how we can actually use a technology that's been designed, you know, for protection applications to look at what else we can do with that. So that gets us into then kind of more condition monitoring. So in terms of offshore inter-array cabling or export cables, whatever, you know, there's the ability there to actually look at being able to identify faulted cable sections and, you know, be able to activate, you know, closures, whatever, on individual cable sections, you know, within that millisecond time frame. We're taking that data as well then over a longer time frame. Let's say, for example, like when we talk about threshold alarms, we're looking at termination monitoring, because that's a combination of temperature sensing and current sensing and ambient temperature sensing, and looking at, you know, at what gathering data from multiple sources before I produce an alarm. Again, data that's actually being produced by the system can actually be used to improve the real-time thermal rating, whatever, of the system. You know, we can also look then at, you know, even with the high sample data rates then for power quality analysis, so detailed kind of study of harmonics, looking at harmonics, you know, at source. We'll look at some of those applications in the next slides. But effectively gathering data and actually using that pool of data and resource then to be able to define the analytics that are actually required to say, yeah, an odd man out, say, this is not behaving the way that it should, this is not behaving the way that others, or we would expect them to, and be able to provide condition-based maintenance decisions on that footing. So one example that I want to look at here is when we talk about termination monitoring. So terminations are actually recognized as a point of failure. So in explaining this diagram here, so we just look at how we would instrument a single turbine or whatever at the transition piece. So we have current sensors there deployed on the output of the transformer. So in this case, like the high voltage side, the 66 kV side. So we're monitoring, as you can see from the diagram, the phase current, whatever, of each phase. We're also monitoring the temperature on the outside of the termination boot, and with the ambient temperature as well. So that's repeated at each turbine. So all of that's effectively a passive system, and we connect the fiber through patch panel. So this is, you know, the fiber, there's a patch panel available in the transition piece, so we can effectively just connect in the sensors directly into that patch panel and move on then on the fiber to the next. So it's a totally passive solution. So this concept of actually looking at synchronously monitoring each termination, you know, in terms of the termination temperature, or the outer temperature of the termination, the ambient temperature, and we correlate that, you know, with the per phase currents and the harmonic content of that, to look then for these outliers, you know, that and we anticipate that then through, or we're also monitoring the load changes of the total circuit, you know, right across field, and that's enabling us to provide earlier warning of these outliers, whatever, in terms of terminations, and you know, be able to effectively provide what is again a real-time thermal rating for terminations as well, because those are effectively the bottlenecks in the circuits. And you know, if we're applying real-time thermal rating, certainly to inter-array cabling, those would actually be more where the bottlenecks would be located as opposed to within the cable. So that's another reason for extending the monitoring, you know, from cable to terminations when it comes to real-time thermal rating of those circuits. So when we're looking at power quality monitoring, you know, so at the point of common connection to the grid, you know, there's stringent requirements on power quality. So the addition of kind of remote voltage sensing and possibly current sensing at defined locations along the turbine string, not just actually on the turbine string, but also could actually be applied on the offshore substation and through to the export cable to onshore connection. You know, so the idea is, you know, to record and track changes in harmonic signatures from turbines, you know, across the field, and kind of identifying outliers, whatever, within that. So that enables a kind of a synchronous and permanent monitoring solution to be deployed to provide kind of deeper insights, you know, identifying the problem at source in terms of harmonic content. Another application that certainly we're looking at here is sheath current monitoring. So in addition to you know, this termination monitoring, we also could provide additional sensors then on cable screens. So it's this concept by continually kind of comparing sheath currents with between phases in relations to phase current, across the entire circuit. We can detect anomalies and changes over time. Those are caused by changes in impedance and resistance, because that can vary over time, and again, that's hugely affected by the load at the time. So we're actually using that then to identify outlier signals. There could be a symptom of cable termination, degradation, and actually knowing those changes in impedance and resistance and how it's reflected in changes in current allows us or enables us a way to distinguish or actually categorize between these pending faults. Whether it, if it's like a screen continuity fault, or wet fault, or other changes in impedance that would actually cause flashing faults, whatever, like from screen to screen. So the data is there to be for us to be able to provide like a level of insight into kind of cable condition that's really kind of not been available before now. So it enables much better insight and a more effective condition-based maintenance platform. So just an example then of the type of data that that's extracted from these systems, in terms of current or voltage, phase angle, frequency, change of frequency, total harmonic distortion, and this through our synthesis software. So it's the means of actually gathering the data and processing that. We can set alarms on that data. We can set alarms on, from data external to the system as well, or we can change that to, reflect some sort of GUI that, that a customer may require. But effectively that data then can be displayed or handled within our own system, or, it can be handed over to a third party. So how can we combine this DES data with conventional monitoring systems? I think I'll leave that for Callum to take over and explain a little bit more about how ECG operates.
Proserv as an organisation harks back to the 1960s with CAC before Proserv Technologies came into being in the early 1970s. Eventually moving to 2011, Proserv Technology was rebranded into Proserv that we know today. But I want to focus on from 2020 onwards, which is when we started to develop our strategic partnerships with both Intelligent Plant and Synaptec, which is the most important one for today, which has allowed us to develop our digital and renewables portfolio. I can't believe I was on mute. Sorry, there's a wee bit of a delay as well as I try and flick through these slides. We're getting there. So as I've mentioned, Proserv, we work across the entirety of the energy sector with controls and system integration right at the heart of everything that we do. And so our goal is to kind of pull those data sources that aren't used effectively, that aren't integrated effectively, and try and pull them into much broader systems that are integrated together, that we can correlate data with the goal of providing users a much more intuitive system to make informed decisions and take informed actions when and where required. Hopefully this promotes safe and reliable operations. And we've had a big push recently into the data analytics space. And that is all about how can we reduce operational expenditure by shifting that needle from reactive maintenance into predictive maintenance where possible, and hopefully reduce the opportunity or reduce the need for maintenance in general by being able to intervene remotely at a much earlier stage. I'm back into my flow now. So Saul is just about to launch a poll for us in the background, and today obviously we're talking about subsea cable monitoring. So I am interested to get your views, listeners, or yeah, webinar attendees of what your perspectives are and the kind of main three challenges that you see. So we've talked a lot about cable terminations, and failures represent about 70% of failures that currently aren't captured by existing or more traditional cable monitoring strategies. There's no clear way to look at cable integrity and performance from a degraded perspective, so it's very, very difficult at the moment to get a good understanding of what a cable's actual health looks like at any given time. This leads slightly into the next one, which is it's very difficult to identify a fault early enough to identify that it is going to become a failure at some unknown point in the future. It would be great that if we could start to put a timeline towards those kinds of failures. The fourth one, inability to make informed real-time decisions due to lack of correlations between different technologies. So I've mentioned that I think system integration is such an important piece of the puzzle. We've got a lot of good systems out there, but they're not communicating with one another. And then the last one there is a little bit tongue-in-cheek from an operator's perspective. Where is the incentive for me as an operator to intervene if I'm well insured and I could hand that back to the insurance organisation as well? So I'll just give everyone a minute to answer the poll if you've not done so already. Saul, I don't know if you want to jump in and chat through some of the results.
Yes, thank you for that. So just for everyone's awareness, most people have already answered, which is grand. I really appreciate that.
Now, Saul, I can't hear you.
Okay, hopefully you can hear me now.
No, can you hear him, Chris? And maybe it's just my end. Sorry, I don't know if the attendees can hear.
Callum, I'll summarise very quickly and just say that the least popular choices out of this were the ability to consult in real time to make decisions, or wait, of course, for to make a claim. No one really wants to do that. That's not good operating practice. Interestingly, the most important one for everyone here is the lack of early warning on impending failures, coupled with specific focus on termination failures, which is just what we want. So very good to hear that, because hopefully you'll find this is very relevant to those key items. So thank you for that, and we'll share some more information about that afterwards. Callum?
Thanks, Saul. Yeah, I appreciate it. I'm not sure what's going on. What's going on in my head? Give me 2 seconds. So hopefully, yeah, I can see the results of the poll. I know Saul's just chatted through. So moving on to the electro cable guard itself. So Proserv's background, our history is all focused on building or bringing proven systems together integrated way so that we can correlate the data and maximize the benefit of that data as well. So today, obviously, we've got a big focus on the distributed electromechanical sensors, but we are correlating that with distributed temperature sensing, distributed acoustic sensing, and any other sensing that is required on site by an operator. But I think interestingly as well, we can pull in like environmental data and AIS data, which should just provide a little bit of extra context around if a sudden failure takes place. Is there a vessel nearby? Is there a chance that, you know, an anchor's dredged and caused that immediate failure? So it just gives us different parameters to get to that root cause, working with the systems that we've got in place. The key benefits, I've probably touched on some of them already, and hopefully they relate quite closely to the challenges that we've proposed within the poll itself. So we want to increase availability, maximise power transmission, reduce failures as a result of the intelligent monitoring, and also to provide that early warning when a fault starts to propagate, that we can identify it early enough and say, as Chris mentioned earlier, that data doesn't look quite right, something's happening there, and can we drill down into that data a little bit more? Also, what we can deliver with ECG is if we identify a fault, then we're able to provide you operational insights on how to utilise that asset and essentially plan the best time from the most cost efficient and resource efficient perspective for you to intervene, and if a repair is required, that you can dive in and do at a time that essentially suits you best, rather than at the moment, which is a bit more reactive. I guess most importantly, just want to highlight that it's such an important asset: subsea cables, export cables, inter-array cables. If a system can provide you that peace of mind about the condition and integrity, it makes the rest of your operations that little bit easier. I can see I'm having some sound issues. I'm really not sure what's going on, so I apologise. Hopefully it picks it up on the recording and the audio. If not, happy to chat it through with anyone else at a later date. I also want to just reiterate that this isn't just for new development. It's easy enough for us to integrate this with existing hardware and install, you know, the additional DES sensors and install the integrated solution on existing offshore wind farms as well. So just to summarise the existing situation at the moment, so you might have a number of different systems that are being fed into the control centre. You've got a control engineer that's trying to make decisions based on that data in real time, and certainly easier said than done. It means that some faults won't be identified or can't be identified early enough, which means sudden failures can and will happen, resulting in substantial costs and downtime associated with those failures. Where we want to move that to, try not to double click, where we want to move that to is from, as I mentioned earlier, from that reactive perspective into the predictive space, to take those isolated monitoring systems and combine them into a much more holistic offering, and ultimately reducing your operational expenditure associated with cable faults and failures. And so on the right-hand side of the screen, what you can see is the HMI of ECG. So in an absolute ideal world, you'll take that top right screen and you'll never have to move off it, because it will always show that your cables are in perfect health. However, if something goes wrong and an amber connection appears, you can drill down into that data. It will show the alarms that have gone off or any events that have triggered that amber status. You can dive into the acoustics, the quality, whatever it might be that will give you the context of the fault, and hopefully prevent that failure getting to a point of, you know, complete collapse. Excellent. So what we've got here is essentially a really simple topology example. So Chris has already chatted about how it works from the integration of DES and how that can be deployed. What we do is we, on the offshore substation, we'll incorporate that interrogator with DTS and DAS across all the strings. And I just want to reiterate that this is a completely scalable approach, so no matter how many wind turbines, no matter how many strings, we can build a system with the suitable specifications that will allow you to monitor it in great detail. And as an organisation, we're completely agnostic to whatever your preferred vendor would be. We can integrate it into the ECG system without any challenges at all. So just to finish up then, I just want to highlight what the ECG is trying to pull in together. So we can pull in inspections and ROV data, combine it with the DES system, any distributed sensing or partial discharge monitoring, we can build it into the ECG to give you that full end-to-end view from normal operation up to failure of the cable, to hopefully give you enough oversight and hopefully definitely give you the foresight to see when a fault is likely to take place and when a failure is, and give you the timelines of when that failure is going to take place as well. We are at Global Offshore Wind. We're sharing a stand with Synaptec. Please come and visit us at stand 39. It's just by the innovation stage. If you're not going to global offshore wind, please feel free to reach out directly to myself at Proserv or Chris or Saul at Synaptec, and we can dive into this in a lot more detail. So thank you very much. I'll hand back to Saul for the Q&A.
Thank you, Callum. Much appreciated. And thank you, everyone, for listening in. And I hope you found that useful. Our goal here was to try and explain that there's a technology that's now available that can give you this discrete, permanent and synchronous monitoring of some very remote and inaccessible locations, which are critical in the pathology of the failure of power cables. Too much perhaps to absorb in one conversation in one session here. So please come and engage with the team at Global Offshore Wind. Now, in the background, there were some questions that kept popping up, and I thought it would be worth taking a few minutes at the end of this session just to cover off the most important ones. And I'll try and read these back to everyone and make sense of them. If we don't address your particular question now, I apologize. We'll come back to you offline afterwards if we run out of time. But one of the first questions, which I thought was useful, it was to understand the difference between DTS and DAS on one side and what we're doing with distributed sensors as opposed to distributed sensing on our side. And I would say the quick way to explain that was that if you think of DTS and DAS, they're using the fiber within the power cable as a very long extended microphone to listen for things and events happening along the length of the cable. What our technology does is use that optical fiber not as a microphone straight away, but as a network to reach out a long distance and put sensors in specific locations. So we do point sensing of things like temperature and strain, not lengthways with spatial resolution. And so we complement and add to DTS by being able to put spot sensors on things like the Fistera box or the T-boots or on a transformer or a cooling system to give you a direct measurement of a critical point in the network where we know there's a high chance of a failure or where we've got concerns about engineering quality and installation quality. So that's probably the key difference. We use the optical fiber as a network to communicate back to our central interrogators from an array of spot sensors, and they're just using light to and fro in the fiber to make that connection without any data. So I hope that goes some way to explain that one. There were also some questions about the type of fiber that needs to be used. Fortunately, we can use single mode optical fiber. So that's the standard single mode optical fiber that's embedded in with the power cables in all subsea applications. So that's why this is a useful technology, because the fiber reaches all the critical locations we want to monitor. And when the fiber comes up in the transition piece, we can access it, as Chris was saying, through the hang-offs, through the patch boxes and the fiber panel. So quick access to the fiber. We can put sensors wherever we need them and then take the fiber along to the next location. So we're utilizing the fiber as a pre-installed network for our sensors. That's what it is. And that works very well already. We've tested this 3 times now offshore and deployed it 3 times, I should say, in offshore wind on subsea cables. And then one other that I thought was interesting to share with the group here was about the type of sensors that are possible. So we mentioned, and just to repeat, within the Synaptic domain, we can do voltage and current, but also temperature, vibration and strain. There are other FBG based sensors on the market which would enable us to measure things like pressure or moisture, but they are potentially compatible. And if you have a particular requirement, please come to Chris and to the team and we can talk you through exactly how they work and what the considerations are around deploying them. But these ones, temperature, vibration, strain, we have deployed in transmission and we are deploying in offshore wind. And so they're already kind of qualified and part of our system. That said, the other question was about where these sensors physically go. So there are questions about, could you put them out in cable joints, you know, in subsea? Would they work, for example, in within a repair joint, or perhaps with the CPS, the bend stiffener? And of course, then in that case, yes, because fundamentally the point of contact where we actually make the measurement with our sensors is just a 2 centimeter strip of fiber with some clever devices etched into it by a laser. And our electrical sensors are incredibly small. They're about 4 centimeters by 2 centimeters, and apologies for the terrible camera angle, but that's one of our sensors with just a pigtail of fiber coming out each end. It literally fits in the palm of your hand. Now that's important because this technique is able to work in subsea. It was developed for nuclear and for monitoring subsea pumps in oil and gas. So the environment doesn't matter to us. In fact, FPG sensors are working on the Mars rovers right now, millions and millions of miles away from Earth in the worst conditions imaginable, and they will function perfectly well because they're immune to temperature change, environmental impacts, or EM interference. So super robust and able to go just about anywhere. The question is, where do you need them, and how would we package that sensor to make sure that it lasts in the environment you need it for? Chris, is there anything else worth commenting on above that?
No, I just think that the vast majority of additional kind of measurements that we normally look at are kind of pressure or input switches to look at, like door status or rotational kind of switches as well. All of that can actually be done passively as well. So you'd be surprised at what additional sensors could actually be put onto that.
Okay. And a last question that I thought might be worth mentioning for everyone here today is about the kind of cables that this deploys on. So yes, it's ideal for intra-array cables because we can take each individual cable as it goes and monitor what the content of that cable is electrically and understand whether the power injection, the quality of injection from each individual turbine is good or poor, and therefore you can work out where the source of your problems are and where power quality problems originate from, so that you can actively filter those out and remove those problems at the source. But also this technology applies to export cables because they're not continuous. You've got subsea sections, you've got the link box in the beach, you've got the underground section all the way through to the grid connection, and any of that can be sectionalized so you can understand where faults are brewing, and where you've got potential thermal limitations or bottlenecks in your thermal rating if you're trying to drive them more dynamically. So it almost doesn't matter where you put these. The more sensors you put out there, the more discreetly and accurately you'll be able to differentiate what kind of problems are occurring where. And again, because it's instantaneous and it's permanent, you'll constantly be able to see live, literally at the speed of light, what's happening in a very remote location. And because of the way that ECG works, you can bring that together in a view with other legacy systems like a DTS system to bring further confidence to your decision making and respond to events in real time before they get out of control. That's really the goal here. Okay, I think we've covered all of the other questions. There are some last ones here about data management and the interface and how the URLs work. Now, we deliberately avoided that in this session today because that's a very deep conversation, but fundamentally you have operational data, we're contributing towards it, and whether you host that data or we find a secure cloud environment to host that data in is really a matter about your IT principles and operating policies, so we can adapt to any of those situations and either work on premise or in the cloud, depending on your data management requirements and your security policies is probably the most important thing. But the screen grabs that you saw from Chris, at least, those are simple web browser interfaces where you can see this data online instantaneously from a standard computer or any web browser. And we natively publish this data in IEC 61850 sampled value format. That's 61850-9-2 SV. That's the standard in the power industry for digital communications and how you package and format and deliver this data. So knowing that means it's compatible with protection and control systems, SCADA systems, and also easily interoperable for other applications. And it will easily interface through an API with any other kind of condition-based monitoring or application that's to do with kind of asset performance management, if you will, from people like IBM, for example, where we know they're very big in this space. Okay. I think just to be respectful of everyone's time, we should probably stop ourselves there because we could spend all day talking about this. And the point is, we do spend all day talking about this. So come and talk to us about this at Global Offshore Wind. It would be great to see any of you if you're available there. Again, this session was recorded, and we will provide a recording of this within about 48 hours, so you've got a chance to review it next week and understand it better. But clearly the goal today was to provoke your interest and your thinking, and to understand that there's technology available now to give you much more granular and discrete visibility and control of these really complicated but critical and remote assets. And we hope that inspired some thinking, and you'll come and engage with us at the event and ask us about what your challenges and issues are, so that we can help you remove cost out of your business and fundamentally improve safety and visibility and control and availability, whilst reducing outage costs and even your scheduled maintenance costs. So with that, many thanks to Chris, and also to Callum for joining in with us today from Proserv. Thanks to all of you for taking your time out of your day to listen to us. We hope it was of use, and we'll be in touch with you very soon to follow up on any inquiries that you've got. So thanks everyone, and have a wonderful weekend.
Thank you.
Thank you.